Hey guys, welcome back. Day 33. We'll talk about concentration today and solution stoichiometry. So to begin, let's dive in with solutions. Talk about a solution. What are we talking about with a solution? Well, it is a homogeneous mixture. These homogeneous mixtures, now typically, our book doesn't go into this, but usually you're looking at sizes of less than 1 nanometer. So my particles are less than 1 nanometer in size. Bigger than that, they become colloidal suspensions. These cannot be separated on standing. They don't separate on standing, and you can't filter out particles. Paint would be something that's not a solution. Right? A lot of paint you have to mix. You stir it up, whatnot. So our solutions are going to be pretty dilute and small particles. And the solutions are going to be composed of two different components. You're going to have the solvent, which is the major component, and this is what the solute is dissolved in. It does the dissolving. Then there is the solute, which is the minor component. And then this is what gets dissolved. Typically, we're going to deal with aqueous solutions. And this is where water is the solvent. So in our, Chem 1, Chem 2, mostly aqueous. And so the solvent will be mostly water. Now, obviously, if you're at home, you know that sometimes you'll use like paint thinner or different organic solvents, whether if you're doing something that's more of an oil-based situation instead of water. So water, though, for our purposes, will be the main solvent. Now, when we talk about solutes, there's two different types of solutes in three categories. The solute is really going to be broken down into two categories: electrolytes and non-electrolytes. You might have heard Gatorade has electrolytes or Powerade. Well, electrolytes, what this comes from is if you had a beaker, here, and this beaker has a solution in it, has some type of liquid, whatever that liquid is. If you had a battery, let's just call it 9 volt, but it doesn't matter what the battery is, let's say, and clip, and you had a light bulb here. The question is, does this light go on or not? So non-electrolytes, the light doesn't go on. Electrolytes, the light goes on. That's the difference. That's all that means. So that means this solution, this blue solution, either conducts electricity or does not conduct electricity. That's all that means. Now we know electrolytes, nowadays we have ions versus no ions. So the non-electrolytes will be our molecules. So let me write that down here in green. So our molecules, our atoms, our solids, our liquids, our gases. So S, L, G, right? Big molecules, little molecules, they're the ones that are not going to conduct electricity. Electrolytes conduct electricity, and electrolytes are broken down into two different categories. We have strong electrolytes and weak electrolytes. Well, what's the difference? Well, strong electrolytes, the light bulb is bright. Weak electrolytes, the light bulb is dim. Well, what does that mean in terms of the actual behavior of the species in the solution? What does that mean? So strong, we now know that there are lots of ions in solution. And we have near complete ionization or dissociation. Whereas weak electrolytes have few ions in solution, which means there's very little ionization or dissociation. So what is this ionization or dissociation I'm talking about? Well, let's look at a strong electrolyte like HCl. We say this is near about 100% or so. All right, it's strong, going to H plus and Cl minus. Or, depending on what definition we're using, you can use HCl plus water, still strong, going to hydronium and chloride. That would be a strong electrolyte. Okay, 100% going over. So it means in the solution, in the beaker, it's all hydronium and chloride. A weak electrolyte like HCN, hydrocyanic acid plus water. Okay. This is, now I'm going to say around 10% or less. It depends. Some are more than 10%, some are less than 10%, and there's a way to calculate it. We don't go over it in our Chem 1 class. There is a way to calculate the percent dissociation. In Chem 2, we quantify it. But right now, all we need to know it's weak, and it's not many go. We got H3O plus and Cn minus. Okay, that's the strong weak. So most of the beaker now is still here with HCN and water. Now, obviously, water, even the strong with HCl, there's a lot of water in the beaker. Water's everywhere. So the better picture of this would just be HCN going to H plus and Cn minus, because water's everywhere still. But we have more HCN than H plus and HCN minus. So that leads a little note here. It might be a confusion. And we'll get over when we get to acids and bases. For our purposes, H plus and H3O plus are going to be the same thing. Interchangeable. Okay, for our purposes. So strong, weak, all that has to do with, do the ions separate in water or not? Okay, the light bulb dim for weak, the light bulb bright for strong. And it's kind of like, I always use this analogy, it's kind of like humans, not human behavior again, not with Adam behavior, but humans. When I went to a junior high dance, it was a big deal to go with somebody. I don't know why, but it was a huge deal, because we get into a bunch of us would get into somebody's minivan, and somebody's parent would drive us to the dance. Everybody get out, big deal. You walk into the dance, and me and my friends would all go to one side of the dance floor, and all the girls would go to the other side of the dance floor, and we never even hardly knew each other were there, except for a couple times we bump into each other, and then we go home for the night. And that was it. That was the difference. That's kind of like strong electrolyte behavior. We're both there, but we're kind of in our own little world, not even paying attention to each other. Weak electrolyte behavior is more like a prom, where you have chaperones separating people at the prom, right? They're sticking together. I'm not trying to make fun of anybody here. I just, as a visual analogy. So strong electrolytes, right, separate completely. Weak electrolytes do not. Most of them do not separate. So now the question then becomes, how do I tell if I have a strong electrolyte, a weak electrolyte, or a non-electrolyte? Because that's kind of important to recognize which one's which. Well, first of all, for strong, there are 7 strong acids in this course. They are the 3 middle halogens, hydrochloric acid, hydrobromic acid, hydroiodic acid, one with 2 protons, sulfuric acid, nitric acid, chloric acid, and perchloric acid. Those are the 7 strong acids. All right, and of course the acids, what does the acid do? It produces H plus or H3O plus in solution. Then weak acids will be all other acids unless told, unless specified. Because, of course, there are more than 7 strong acids in the world. So the weak acids, HF, HCN, H3PO4, H2CO3, HNO2, HC2H3O2, and it goes on and on and on. Now I want to point something out. When I was in your shoes, I thought strong meant dangerous because there's a lot of H plus in solution, and weak meant not dangerous. And that's not the case at all. That's not the case at all. We have a roughly 0.1 molar solution of HCl in our stomach right now. That's good. We would not want a 0.1 molar solution of HF or HCN in our stomach. That would be very, very, very bad. Okay, so just because strong, all that has to do is their behavior in water. All chemicals can be inherently dangerous, and all chemicals can be inherently safe, depending on how they're used and how much and all that. So HCl would be a strong acid, but it's not necessarily as, per se, toxic as some other ones. So it just depends on a lot of factors. So just know, strong means more H plus in solution, better conductor of electricity. Weak means less H plus in solution, less of a conductor, but it has nothing to do with how dangerous, toxic, deadly, non-deadly, none of that. Okay? So don't think strong, dangerous, weak, safe. That's what I thought when I was in your shoes at first. That's not what that means. It just has to do with how they conduct electricity. So those are the acids. So there's 7 strong acids, and then there's everything else will be weak unless otherwise told. Then we got strong bases. And these produce OH minus hydroxide in solution. Okay, and they're going to be their group 1 and 2 hydroxides. Now this definition gets expanded in Chem 2 to hydroxide. So basically in Chem 2 it's hydroxides, oxides, and sulfides. But in Chem 1, which is group 1, group 2 hydroxides, so that would be lithium hydroxide, sodium hydroxide, potassium hydroxide, with sodium and potassium being the common ones. Now, rubidium hydroxide and cesium hydroxide are strong bases, they're a little too strong to use, a little too dangerous to use. They dissolve beakers and stuff. We're not going to use those in the in a lab setting. So, but they are strong. You see them, they're strong, but we probably wouldn't be using them. Beryllium hydroxide, that one is not a base. It's covalence. Let's spell base right. Not a base. Then we have magnesium hydroxide, calcium hydroxide, and to be honest with you, CaO is lime. That's probably the most common base that we use because it raises soil pH. We also have strontium hydroxide and barium hydroxide. Now they're strong because they react 1-to-1 with an acid, but they don't dissolve well. The two most common ones, again, are sodium and potassium hydroxide. Those are your two most common strong bases that you would use in a lab setting. Weak base is ammonia and its derivatives. So that's obviously NH3, but anytime you have N has this lone pair, and it doesn't matter what 3 bonds it has, that's a base. That's a base. So anytime you see, X, Y, Z, N, that's going to be a base. You'll get to in Chem 2, we'll put X, Y, Z, N, H+, and that's an acid. But right now, that's going to be a base. Okay? That's a base. The last thing that are strong electrolytes are salts. All right? These are any soluble ionic compounds. If it's aqueous and ionic, so MXAQ. So if that's not a soluble salt, if it's not a strong base, strong acid, weak base, it's a non-electrolyte. So all our molecules are non-electrolytes. This leads us to concentration. Concentration is a ratio of solute to solvent or volume. So it's a ratio of solute to solvent or volume. It's a ratio. So it just gives us a quantity to use. We'll be using molarity. Molarity is a ratio of moles of solute per liters of solution. And that's a total volume. We will abbreviate it with a capital M. Okay, it's a ratio of solute to volume. So you'll see it a lot of times just written as, 4M, which equals 4 moles per liter. But it's 4 moles of solute to 1 liter of solution. It's also moles per 1,000 milliliters because 1,000 milliliters is 1 liter. And those of you who are very comfortable with the metric system can use millimoles per milliliters, and that'll work too, because if you think about it, milli means 10 to the negative third. Milli, I'll do milli like this. Millimoles per milliliter is the same thing as moles per liter. So you're allowed to do that too, however you want to work with it, because we will use milliliters a lot, and we will be using small concentration, small amounts. So millimoles is actually not a bad thing. So you can use millimoles per milliliter. That works too. The reason we like this, before we do this example here, is that a volume, like milliliters, a volume, multiplied by our molarity, for 1,000 milliliters is moles, give me moles. And so when we do calculations, when we do stoichiometry, if I have a volume, which is something I can measure, so I have my measured amount in my volume, times my molarity, my concentration, gives me the moles that I'm working with. Now, one thing I need to mention before we do this example is that volume, for both, this volume and the right here, this is temperature dependent. All right, volume is temperature dependent. So we have to keep that in mind when we're actually doing stuff, when we talk about, well, what's the concentration? Well, at 25 degrees Celsius, that's the concentration, but what at 15 degrees Celsius? The concentration may change, right, slightly. Not huge amounts, but slightly, depending on how much the solvent changes. Let's do our example now. Calculate the molarity of a solution prepared by dissolving 40 grams of sodium hydroxide in 2 liters of water, which is the total volume. So we have 40 grams sodium hydroxide and 2 liters of water, which is the total volume. Okay, so we have 40 grams sodium hydroxide, NaOH, and let's just pause. If we're still having trouble naming, go back and review that. Review your polyatomic ions. You need to know them for the course. Because when you get to a test, if you have to look them up and you're not recognizing them, it takes you longer. You'll run out of time. You got to know them. Flashcards every day. You can do it on your phone too. The flashcards. So we have 40 grams of NaOH and 2.0 liters of water. Now, the 2.0 liters is what we want. Check. But we need to get grams here to moles. I think we can do that. Turns out that sodium is 22.99, oxygen 16, and hydrogen's 1.01 grams per mole. So you add those up, you actually get 40.00 grams of NaOH is 1 mole of NaOH. So now we're in moles per liter, which is great. So that becomes 0.50, because I only have one sig fig. So 0.5 M NaOH, and that's my answer. That is molarity, and we'll be using molarity a lot. In fact, you use molarity in Chem 2 all the time as well. Next topic, dilution. Dilution. Now, this is something that happens naturally. And where I live, there's Sonic, and Sonic gives you, some people call it the good ice, but it's crushed ice, and there's a lot of it, which is fun if you get a Sonic drink, and some people really enjoy that. However, in the summertime, what happens to that ice? It actually melts and becomes liquid water. It goes from solid water to liquid water. But what happens is you're diluting your drink, whatever your drink is, because they have a bunch of drinks. And so their drinks get diluted with water. So what is a dilution? Well, for our purposes, right, because again, the Sonic does this, McDonald's does this, they buy their soft drink syrup as concentrated as possible, because shipping does cost money, contrary to what Amazon says. Shipping does cost a lot of money. So many solutions are made and transported as concentrated as possible in forms called stock solutions. For example, my mom used to buy orange juice, Minute orange juice, frozen. And you had to put it into the pitcher and add the water to make your orange juice. My wife doesn't do that at all. That doesn't happen. I don't happen to drink orange juice, but she does it. It's always the not from concentrate. Well, some people do buy it from concentrate because it's a lot cheaper. We buy here at the college, we buy hydrochloric acid, prime example. We buy it as concentrated as possible, which is just over 12 molar. Because you can't get hydrochloric acid as a solid, it's a gas, so it's dissolved in water. So we get as concentrated as possible, and a lot of times we do dilute it for use. And so in this case, these for HCl and a lot of other things is that they may need to be diluted for use. All right, so now in this, I want to put in a little note. No reactions here. The moles of solute do not change during the dilution. The volume does. Right? So if you go back to your Sonic drink, the amount of, let's say Coca-Cola, Pepsi, whatever they put in there, I don't even know. Let's say whatever soft drink they put in there, that's a fixed amount. As the ice melts, the amount of soft drink you have in that cup does not change. The amount of water increased as the ice goes from a solid to a liquid. So the amount of soft drink doesn't change. The water does. The volume of water does, because the ice doesn't count as the volume of water. It's solid, and then when it melts, it becomes water. It does add to the volume of water, so you technically dilute it. So what happens here is that you have molarity times volume equals molarity times volume. And so molarity 1, volume 1 equals molarity 2, volume 2. The units for molarity are obviously molarity. That's what it is. The volume just has to match. You could do gallons. If I go from 1 gallon to 2 gallons, it doesn't matter. I doubled the volume, I have the molarity. Most of the time, though, our volumes will be in liters or milliliters. They just have to be the same units, V1 and V2. So here's an example problem. What volume, there's your question, of a 12 molar solution of HCl, there's my concentrated HCl solution, must be used to prepare a 0.5 liter solution of a 4 molar, half a liter of 4 molar solution of HCl. So it's the dilution. There's no chemical reaction. M1 V1 equals M2 V2. On the side here, M1 V1 M2 V2. What volume of a 12 molar solution? So 12 molar would be my M1. V1, I don't know. M2 is 4 molar. And V2 is 0.500 liters. Just plug in. 12 molar. We don't know. V1 equals M2, 4 molar, and 0.500 liters. We solve that, divide both sides by 12. V1, I get 0.17 liters, or 170 milliliters. So that is dilution. So now let's do our examples for day 33. In history, the photographic development process, right? People used to have cameras with film in them. I know I did, and my parents did, and your parents, and right. Nowadays, we just have cell phones. Like your cell phone pretty much is your camera. Now, some people have very nice cameras still, and they have, they take pictures, but it's almost all digital now. There's very little film being developed. So silver bromide is dissolved by adding sodium thiosulfate. If you want to dissolve, 0.225 grams of silver bromide. The question begins, what volume of 0.138 molar sodium thiosulfate in milliliters should be used? So is my equation balanced? Well, there's a 2 there, so it should be. I have 0.225 grams for my sodium thiosulfate. I have 0.138 molar, and I want to know how many milliliters. What's the volume? What's the volume going to be? Okay. Is this a limiting reactant problem, guys? Well, no, it can't be, because I don't have information for sodium thiosulfate. What do I have all the information? Silver bromide. So we're going to start with our 0.225 grams of AgBr. First up, let's go down. We have to do the molar mass. So silver bromide's molar mass is 187.77 grams of AgBr is 1 mole of AgBr. So there's 1 mole of silver bromide. Next up, what has to go on the bottom? Moles of silver bromide. And then we want moles of sodium thiosulfate. And the mole ratio, 1 to 2. And here's a new step. What has to go on the bottom? Moles of Na2S2O3, moles of sodium thiosulfate. On the top, what do we want? We want liters, or in this case, milliliters. 1,000 milliliters. And I have 0.138 moles. So what do we have here? Let's recap. This is my amount in grams. This is a molar mass, which is a ratio. This is my mole ratio, which of course is a ratio. This is our molarity, which again is a ratio. And this is going to equal, if we do this math, 17.4 milliliters, which is an amount. So we go from an amount in grams to an amount in volume. 17.4 milliliters of our 0.138 m Na2S2O3, sodium thiosulfate. That's all that is. Next one, number 2. What volume of 0.750 molar lead 2 nitrate in milliliters? There's our question. What volume of this guy in milliliters is required to react completely with 1 liter of 2.25 molar sodium chloride solution? Okay, what's the hardest part now? What do you think? It's coming up with the balanced chemical formula. That's the hardest part for everyone. It's not going to be the math here. It's going to be the hardest part is, what is my chemical formulas? So I have lead 2 nitrate. And in this point, what's lead 2 mean? I have Pb2 plus, nitrate, NO3 minus, sodium, Na plus, chloride, Cl minus. I would recommend doing this. Now put it together. So we have lead 2 nitrate, Pb, NO3, 2. What state symbol will it be? Well, that's a good question. Well, we have 0.75 molar. We have a molarity. It's going to be aqueous. I will tell you if the solution's not in water. Sodium chloride, NaCl, and that's aqueous as well because that gives you concentration. Reacts. Well, it's going to switch dance partners. Right, do-si-do. Pb, and that's 2 plus, Cl's minus, Cl2, and NaNO3. Now, we have yet to talk about solubility. We'll learn that this is going to be a solid for lead 2 chloride, and sodium nitrate is going to be aqueous. Not too worried about the state symbols in this question, right? Because that's not what they're asking, but that's what it is. Now we have to balance. Let's balance. So 1 lead, 2 nitrates, 1 nitrate. I need a 2 in front of nitrate. 1 sodium, now 2 sodiums, 2 in front of NaCl, 2 chlorides, balanced. Put our stats down. We have 0.750 molar, and I need to know how many milliliters. And we have 2.25 molar and 1.00 liters. Is this a limiting reactant problem? Negative, because we don't know the data, the information of both reactants. So which one do I know everything about? The sodium chloride. 1.00 liters of NaCl. What goes on the bottom? 1 liter. NaCl is 2.25 moles of NaCl. Well, what's next? It has to be moles of NaCl. In this case, 2. 1 mole of PbNO3, 2. I didn't go to the molar mass. Did I need to go to the molar mass? No, I do not, right? That's what's nice about molarity. I'm already in volume times molarity. I'm already in moles. Already there. So after my mole ratio, what has to go on the bottom? Moles of lead 2 nitrate. And we want milliliters on top. Do I have a mole to milliliter conversion? I sure do. And that is 0.750 moles of lead 2 nitrate is 1,000 milliliters. So if we do this, I get 1,500 milliliters. That's a lot. That's a lot. So again, recapping. I have a volume, which is amount. Molarity, mole ratio, and molarity. Back to a volume. That's it. Pretty good, huh? Do we have another one? Okay. Let's try another one. When aqueous solutions of sodium sulfate, Na plus, SO4 2 minus, and plumbus, which we learn is lead 2 here, Pb2 plus, nitrate, NO3 minus, are mixed. Lead 2 sulfate precipitates. So it tells us that lead 2 sulfate is a precipitate reaction. So let's write this out. Sodium, Na2SO4, aqueous, plus Pb, NO3, 2, aqueous, going to, we know it's PbSO4, solid, and what's left is sodium and nitrate, NaNO3, aqueous. Is it balanced? Well, let's look. Probably not, because I got 2 nitrates. I need to put a 2 in front of sodium nitrate, and I think now it is balanced. Now it is. Well, that's good news. Okay, let's see what we got. Calculate the mass of lead 2 sulfate. So I want to know how many grams are formed with 500 milliliters of 0.1 molar lead 2 nitrate 500 milliliters of 0.1 molar. Sorry, guys. 0.1 molar. Oh, jumped on me. 0.1 molar of, that's lead 2 nitrate. So 500 milliliters here, 0.1 molar there is, and 500 milliliters, same volume, of 0.25 molar sodium sulfate are mixed. Well, now we have the amount and the ratio of both reactants. Just like if you have mass and molar mass, you always have molar mass, so you have a periodic table. So if you have mass, you have the molar mass, you have the amount and the ratio, you can always get moles. Now we have volume, the amount, and the molarity, the ratio. We can get moles. So now I can get moles of both my reactants. So I have to figure out the limiting reactant. So start off with 500 milliliters. We know for every 1,000 milliliters, I have 0.25 moles of sodium sulfate. Or I could do the math this way. I could go to 0.5 liters times 1 liter is 0.1 moles. I don't care which way we go, how you want to do this. I'm happy either way. And so if we do the first one, right, that would be 0.125 moles of sodium sulfate and 0.05 moles of lead 2 nitrate. The next step is we have to find the limiting reactant now. How do we do that? Well, one of the easiest ways is to take the moles, which I have now, and divide by the coefficient. I used to write that in orange. What are my coefficients here? I'm going to write it out, but the coefficients are 1, aren't they? So if I have 0.125 divide 1 is 0.125, and 0.05 divide 1 is 0.05. That means lead 2 nitrate is my limiting reactant. So we start with 0.05 moles. And now we're going to take 0.05 moles of PbNO3(2), and we'll convert that into lead 2 sulfate. First up is the mole ratio. Because moles of PbNO3(2) have to go on the bottom, and we're looking for moles of PbSO4 up top, and it's 1 to 1. And it looks for grams, so now we're just going to use the molar mass. 1 mole of PbSO4 is, lead is 207.2 plus sulfur is 32.07 plus 16.00 times 4. I get 303.27 PbSO4. And so if we do this math, I get 15.1635, which sig fig wise, I have 2. Well, I really only have 1 with the 500 milliliters and the 0.1. So really it's 20. So I'm going to put down 15 milliliters. But really it's only 20 milliliters according to my sig figs. 20 milliliters of my, 20 grams. Excuse me. Of PbSO4. So 15 or 20 grams, because I only have 1 sig fig. So 20 grams of lead 2 sulfate. One more problem, and we're done. Calculate the mass of solid sodium chloride that must be added to 1.5 liters of a 0.1 molar silver nitrate to precipitate all the silver ions in the form of AgCl. Whew. What are we calculating? Calculating the mass of NaCl solid. So we know we have NaCl solid added to silver nitrate, AgNO3, and that's a molarity, so it's going to be aqueous. We're going to precipitate it in the form of AgCl, so that's a solid, and what's left over? Na and NO3. Let's talk about our concentration here. I have 1.50 liters and 0.100 molar, so now we're back to 3 sig figs, thankfully. So sodium nitrate is aqueous, which is good to know, but it doesn't necessarily matter for this case. And we're looking for how many grams of table salt, sodium chloride, to add. Is it a limiting reactant? No. We'll start with the silver nitrate. And what do I start with? The amount, 1.50 liters of my AgNO3. And we're going to multiply. For every 1 liter of silver nitrate, I have 0.1 moles, 0.100 moles of AgNO3. Is my equation balanced? Did we forget that? 1 sodium, 1 sodium, 1 chloride, 1 chloride, 1 silver, 1 silver, 1 nitrate, 1 nitrate. It is balanced. So it's 1 mole of AgNO3 of silver nitrate to 1 mole of NaCl. And last but not least, we have 1 mole of NaCl. Well, sodium is 22.99 plus 35.45, and that should be 58.44 grams of NaCl. And so we multiply out. I get 8.77 grams of NaCl. And that's how much sodium chloride I would need to calculate or to precipitate the silver ion out as silver chloride. That is day 33. I hope that helps, guys. Take care. We'll see you next time.